So good morning to everybody. And first of all, let me say thank you to the organizers. And also thank you for the suggestion order to give some kind of theory overview. That is what I'm going to try to do, a theory overview of quantum turbulence. So, most information which we have about quantum turbulence comes from experiment with liquid helium, helium-4, helium-3, and atomic gases. Now, those are not the only quantum fluids. There are others which are important, for example, I don't know, neutron stars, polariton condensates, etc. But everything which I say mainly refer to helium and atomic BECs. And I think it's important to consider them together to make progress because they all share the same important properties of quantum turbulence, which are the following three properties. So first of all, superfluidity. So we have to deal with systems in which there is no viscosity in the sense of ordinary fluid mechanics. Now this property is not as important as it may seem at first sight, because there are actually other mechanisms for the vortex lines and the turbulence to dissipate. The second property is more crucial, the quantization of the circulation. This is a consequence of the existence of a macroscopic wave function, psi. You see it written there with the amplitude related to the density of the fluid and the phase, which is related to the velocity field. So the circulation is quantized. That is something easy to demonstrate simply from the existence and uniqueness of psi. And this circulation must be a multiple integer of a quantum of circulation kappa, which is the ratio of Planck's constant and the relevant boson, as you see written there. So this property is crucial because it makes quantum fluids quite different from ordinary fluids in which the circulation and the vorticity are not constrained at all. And the third property is that when the temperature is not zero, we are in our systems, there are also thermal components which we need to account for. So that can be, for example, some kind of dilute gas moving ballistically, or if the mean free path is much shorter, takes the form of some kind of fluid, which we can refer to as normal because that's the name which is used, and also because it's really like a viscous fluid of traditional fluid mechanics. And this fluid may become turbulent too, and that introduces lots of complications and also interesting features. So these three properties come together in both helium and atomic condensates. Now, if we want to make some theory of this quantum turbulence, we need equations of motion to start with. Right, so I want to use two examples. Suppose you're interested in turbulence theory, then how do you start? Well, you start from some equations of motion, provided your Mach number is not large, then you can use the incompressible Navier-Stokes equation, which you see written here for the velocity field, and you move on rather solid ground. You can predict all sorts of things and develop your theory of turbulence. The second example is dynamo theory. So that is the theory which tries to explain the generation of magnetic fields in systems such as the Earth's interior, the outer core of the Earth, or the interior of Jupiter or other planets, or the interior of the Sun and stars. So here you have a velocity field, V, but also a magnetic field, B. So we have two unknown fields, and the equations in the minimal form, they're written there. In some cases, there will be also some temperature equation, essentially producing convection, which drives the dynamo. But in essence, you have two fields and two equations. So the problem is slightly more complicated. Above all, historically, there is a name which has been used in this context, which is the name kinematic dynamo. So what's the idea? Well, being actually the problem quite difficult with two nonlinear field equations to solve together, people started solving making sense of solutions of problems where the velocity field is given, and then they studied what happens to the magnetic field B, or vice versa, given the magnetic field, find what happens to the velocity. So it's kinematic. It was only in the mid-90s really, when computers became big enough that it was possible to solve together V and B. So we have something which we can call fully coupled MHD equations to study our dynamo. Okay, so I make this remark because we'll see that it's relevant to some effects in our quantum turbulence. So what are equations of motion of quantum turbulence? Well, unfortunately, we don't have a simple set of equations of motion to study. We have only somehow a patchwork of loosely linked equations or models which cover different ranges of length scales. And to simplify things, I'll define essentially three kinds of length scales. A macroscopic length scale related to the size of the vortex core, which are called psi. Then the typical scale of the vortex distance, L, the average distance between vortices in our turbulent system. And then there is the large size of the system, size G. Now imagine that your quantum vortices are trees. At the macroscopic scale, you can actually go very close to the tree, put your nose almost against the bark, and you see all the details of the bark. So in a similar fashion, you can go very close to a vortex and try to see what's there, for example, what's inside. And if you use the standard microscopic model available, which is the GPE, the Gross-Pitaevskii equation, you'll discover that essentially inside it is empty. You can also move away from the tree, and then in your field of view, you will see many trees, but you will not recognize all the details of the bark. You only see sticks. So at this kind of mesoscale level, trees are sticks, and you see them. You can count them. You can also move much farther away, and then you don't see the trees any longer. You only see forests. So then the forest, you can distinguish if it is dense or less dense. So that's another level of description, very macroscopic. So we have the models at these three levels. As I said, the Gross-Pitaevskii equation, the GPE at the microscopic level, and then we have another model, the Vortex Filament Method, abbreviated VFM, and then at the level of the forest, the whole Weinand-Beckerevich equation, HVBK. So there are three different descriptions. And below you see some references if you want to look up and see how the models work. I've chosen these three papers. So the first by Norebid and Brachet was actually quite important because it showed for the first time actually using the Gross-Pitaevskii equation a connection to classical turbulence. Essentially they studied the decay of some arbitrary initial state containing lots of energy, a Taylor-Green flow, and spotted that as it decays, the classical Kolmogorov law, the K minus 5/3 law, develops, indicated some cascade of energy, like in ordinary turbulence. The second paper is similar in spirit. So the model used was the Vortex Filament Method and produced the first evidence of the Kolmogorov law using this method. And then the whole Weinand paper earlier, which was very important because it extended the Landau equation for liquid helium to include vortices for the first time. So let's look now more in details at the first more microscopic level of description, the Gross-Pitaevskii equation. So where it comes from? Well, it comes from n-body quantum mechanics, but you need to make some approximations. So in the mean field approximation, you have simply a field, a complex field psi, and the equation looks like that. It is actually something similar to the Schrödinger equation of quantum mechanics, but it is a nonlinear Schrödinger equation. It has a cubic nonlinearity. And below, what you see written is normalization. N is the number of atoms of the system, and then other parameters, you see G, the strength of the interaction. And if there is a trapping potential needed to confine your bosons Well, that is a term in front of, with V and psi. Now this equation, actually, this model is a good model, a good quantitative model. You can make predictions of the behavior of atomic BECs, provided the temperature is much less than the critical temperature. So it's very useful. It has a nice interpretation because using the so-called Madelung transformation can be mapped to essentially classical hydrodynamics. One gets the compressible Euler equation. Better, one gets almost the compressible Euler equation because there is an extra term, which people call the quantum pressure. So as a compressible Euler equation, it describes very well sound waves, and it describes vortices, quantum vortices. I'm going to show you why in a moment. And what is the role of the extra term, which distinguishes Gross-Pitaevskii from Euler? Well, this quantum pressure is quite important because it makes possible to do things which the Euler equations cannot do. For example, you can create vortices. So it describes vortex nucleation and the reconnection of vortices. Reconnections of vortices, vortices colliding and changing and exchanging heads and tails, changing the topology, is clearly a crucial effect in turbulence. So it's beyond Euler. So this is the Gross-Pitaevskii equation. So what is a vortex in this system? The most microscopic, which I'm going to describe. So it's quite simple. I said you can relate the amplitude of the wave function, the complex wave function, to a density and the gradient of the phase to a velocity. A vortex is a very deep hole. The density is 0, exactly equal to 0 on the axis, around which there is a circulation, as it is sketched in those diagrams. So this change in circulation, changing from 0 to 2 pi, going around, corresponds to the superflow around the vortex, a velocity field which is actually utterly constrained. It has this form, kappa divided by 2 pi r, kappa the quantum of circulation. So it's the classical vortex of Euler fluid mechanics, which you see in textbooks. And the fact that it diverges at the origin, it's no problem, because there the density is actually 0. Okay? Psi, the length scale of the core, is the thickness of this small empty hollow region, which I defined as the bark of the tree before. So, how do you go from one vortex to turbulence? You need many vortices, and here you see a picture with many vortices. Actually, it's a computational picture. So the vortices are colored with different colors to show that there are many, and they're all tangled up. So I'm using the term vortex tangle for quantum turbulence at the moment. But we should not forget that together with the vortices, there are also waves. Because when a vortex, in this model, but also in classical mechanics, when a vortex moves, or better, when it accelerates, it generates sound waves. So those are the ripples of the profile of the density, which is indicated there. So that's the most general situation you find. Vortices and sound waves. So the difference is that the vortices are locked in by the changing phase, changing by exactly 2 pi. The waves are not. There are other objects in between waves and vortices, for example, which are interesting too, and they happen. They can be seen. They are solitons, essentially. They are density perturbations, which are big enough to be considered nonlinear, not as big as the vortices, not as deep as the vortices. They have associated a density, a phase change, but that is not constrained. Essentially, it sets the speed of the solitons. So, yeah, I also mentioned this paper by Navar and collaborators, a recent paper, because they produced, actually in that paper, they were studying the turbulence of the waves. Because we should not forget that we can simply have turbulence of waves. But in their paper, it's apparent that together with the main subject, turbulent waves, there are also some vortices. So we should keep in mind that it's almost impossible to decouple the two. And the reason is simply that a vortex is a very nonlinear wave, protected by the topology, this phase, which changes by 2 pi. So let's go back to this picture here, so that is our quantum turbulence or vortex tangle, then the next question is, what is the physical nature of this thing? Because what you see here is simply lines representing the vortex core. So we are naturally attracted by this feature, the core of the vortices, and it's easy to forget that what matters is not actually the line, but actually the flow, which goes around the line, and which moves with that very constrained form, which is this velocity field kappa divided by 2 pi r. So, what is the nature of this turbulent flow? If you look at this picture, your imagination will tell you, oh, well, the velocity field must be very complicated there. But of course, you have no way to tell from this picture. To start with, I've not marked in any way the orientation of the vortex lines, and that clearly makes a big difference. So you can actually try to answer this question by finding, for example, the energy spectrum, which is defined at the bottom. So you take the total kinetic energy and you see what happens, how it is distributed in k space. So how to proceed? You Fourier transform your velocity field, you use Parseval theorem, and then you assume isotropy, and then you turn everything into an integral over k, which is the magnitude of the three-dimensional k wave vector. Essentially, you move around Fermi shells from 0 to infinity, and the density Ek is the energy spectrum. So that is the distribution of the energy over the length scale, where at the place of a length scale, I'm using wave numbers. So what people found, for example, was that a vortex tangle of the kind which you see there can actually have different natures. So there are two limiting cases identified neatly by this nice cartoon by Bolovic. And one form of disorder of turbulence, which he called the Kolmogorov, or quasi-classical, or classical, if you want, in which the vortices are turbulent, they are disorganized, but there is some idea of order there, and he drew some kind of bundles, and some kind of arrangement of the vortices in which they are really random looking, they're loops, and they're totally disorganized in space. And that form of turbulence corresponds to different energy spectrum, and it has been called Wien turbulence, or ultra-quantum turbulence in other papers. So to give you an idea of the second kind of turbulence, sorry, go back. I want to make this example. So the first turbulence, the turbulence which is Kolmogorov-like, which has classical feature, is, by the way, the one which refers to the two papers I mentioned before, the papers by Noor and Araki. But here I want to make an example of this new form of turbulence. So the example is a very rapid cooling of a Bose gas, a thermal quench. So the idea actually dates back to this paper by Berloff and Svistunov. So what they did was to take this idealized system, perfect Bose gas in a periodic box, and they imagined that it cools very rapidly. So they started with the uniform occupation numbers and random phases on essentially in a computation on the mesh. The idea is that the order parameter cannot adjust consistently everywhere. The size of the domains is as small as possible. That's just a mesh point. Yeah?
My question, what's the energy landscape of the vortex tangle? Is it ordered in any way? Is this a metastable state, or?
Well, I'm going to answer that question in a moment. So we'll see, for example, in this case, that this turbulence is indeed metastable, it's decaying. And you see this process of thermal quench, which builds up a turbulence very quickly. So these are three snapshots of the vortex tangles. So this is, as I said, it's an example using the Gross-Pitaevskii equation. So the vortices are these tubes, hollow tubes. What you see in red are the tubes plotted at some arbitrary level of density. So here you see a very, very intense vortex tangle close to equals 0 when the system actually starts forming some condensate forms. And you get turbulence, but the turbulence decays. So it is a metastable state, the tangle decays, the turbulence decays, there are less and less vortex lines. And during this decay, you can study the property. So lacking a significant amount of energy at the large length scales, this turbulence actually will not evolve into a classical Kolmogorov-like turbulence, like in the paper by Nore and Araki. So the energy spectrum is shown at the right-hand side, at the bottom. So energy density versus wave number, and you see these various scalar curves. And above all, let's see. Above all, notice that the shape of the spectrum is some kind of bump. This black line is the energy which is missing. That black line would be the Kolmogorov spectrum, which is not there. So there is quite a significant amount of missing energy at the large scales. So it's quite different from the paradigm of homogeneous isotropic turbulence of ordinary fluid mechanics. And you can identify features, for example, particular decay after the peak, etc. So that's the signature of this Wiener turbulence. And another one would be the typical behavior of the decay. So the decay of the vortex length at the bottom left goes like the time to the power -1. Or another signature would be the correlation of the velocity, which vanishes very, very rapidly, because essentially we have to do with some kind of almost random flow, really. So very unlike the Kolmogorov flow. So that was an example of the Gross-Pitaevskii model. Then let me consider the mesoscale model. So we move away from the bark of the tree. We see the trees, but they're far, so we think of them as sticks. So the model was invented, the model comes directly from classical fluid mechanics, but it was applied for the first time by Klaus Schwarz in the 80s. He realized that the length scale of the vortex core in liquid helium is about 10 to minus 10 meters. So it is immensely, it is about at least 10,000 times smaller than the typical distance between vortices. So the details of the vortex core should be irrelevant. And the vortex lines can be thought as curves in space, one-dimensional curves in space, which here they're written as vector S, position vector, depending on some arc length, which is this zeta, and then time. And he derived equations of motion, essentially balancing the friction and the Magnus force. He found that the motion of the vortex lines is given by this equation, which I can refer to as the Schwarz equation. So there are three terms at the right-hand side. You see that there are two terms with parameters alpha and alpha prime. Those are dimensionless coefficients. They're called the friction coefficients, and they arise because the vortex lines actually scatter the thermal excitations of our system, the phonons and the rotons in the liquid helium in particular. So the components of the normal fluid. So we have this effect. Yes?
So here you are at finite temperature then?
Yes. So this equation is valid at finite temperature. So these numbers alpha and alpha prime, as I said, are dimensionless. So they will be 0 at 0 temperature. At 0 temperature, you are left only with one term, the first. So the STT will be equal simply to Vs. And what is Vs? It will be the superfluid velocity generated by the vortex lines themselves, because around each line, remember, there is a flow, very much constrained, but there is a flow, and you can recover this flow using a classical formula, which is written here. It's called the Biot-Savart law. It's a classical formula. It is mathematically, it's the same problem as the problem of finding the magnetic field generated by current. So that's why it's called the Biot-Savart law. And it's interesting that it's possible to relate this formula to the more microscopic model, the Gross-Pitaevskii model, that has been shown by Bustamante and Mazarenko not long ago. But you can see why it must be there, because you can go from, essentially, remember, the Gross-Pitaevskii equation can be mapped to compressible Euler. Then you can look at large length scales, essentially take the limit of vanishing Mach number, and you must go into this limit. Okay, so this is the vortex filament model, and there is something to note here, therefore, that we have therefore these two limits, t equals 0, which would be simply dsdt equal vs, and that simply restates Helmholtz theorem. A vortex lines moves with the flow generated by all the vortices, and then at final temperature, these friction effects. And in this equation, written by Schwarz, Vn would be the velocity of this normal component, which is prescribed at this stage. So I must stress that this model does not contain sound waves. It is actually incompressible, so we lost this physics. And there is also some other physics which is important, which we lost. It is the reconnections. So the model is based on the assumption that the thickness of the vortex line is infinitesimal to anything else in the problem. So it does not cope with vortex lines which actually come to the point of colliding. So reconnection must be implemented by the algorithm which uses this model. So it's very arbitrary. So that was actually quite an interesting point. It was actually remarked by Feynman before Schwarz that reconnections are important in the turbulence of these vortex lines, and Schwarz really found it the hard way, because without reconnections, he could not actually do anything with this equation. The lines would come close to each other and essentially tie themselves up in some kind of knots at higher and higher velocity without proceeding. So reconnections are important, and there is progress being made recently. So here you see an example of a reconnection. You see these two vortex strands, the red vortex strand and the blue vortex strand colliding and then changing the topology. So I want to refer you to talks later in the workshop during the week given by Ferrari and Galantucci on this important ingredient of the turbulence. So let's make now an example of the vortex filament method. So here we see again another computed picture of a vortex tangle. This is much denser than the previous picture. I didn't try to color the vortices because there are not enough colors here. And in fact, the picture is so dense I can barely see them. It's essentially all black. So the good question is, yes, but I imagine if there is something like that, it must be very turbulent, but I don't know how to say anything else. From the point of view of the experiments, actually, we don't know much either, because experiments in liquid helium in particular detect the density of vortices. They can figure out the total length per volume, irrespective of the orientation. There is a mild effect because the techniques based on second sound don't perceive vortices which are actually aligned in the direction of propagation of sound. So they only see things transversely, but essentially they cannot give an insight inside this kind of mess. So if you do numerical computation, you end up with something like this, and you don't know what you're learning. So you need to make further steps. So at this point, it is useful to try to define a quantity which is the vorticity. Now, the vorticity will be the curl of the velocity field in classical fluid mechanics. In our problem, it seems like a pointless quantity because the velocity is the gradient of a phase, the phase of the wave function, so the curl is equal to 0. So with vorticity, we don't mean actually the classical vorticity. We simply mean a way of describing the fact that we have vortex lines with circulation. So if we want to define in some practical way vorticity, we can do something along these lines, for example. Here you see a formula which essentially tries to dress up the tangent vector at any location labeled by the index j along a vortex line with some kind of Gaussian, with some arbitrary width sigma. So build up some kind of Gaussian dresses and along the vortices and create an oriented vector field, omega, vorticity. The picture which you see at the bottom right gives an example of this procedure. So at the top you see two vortex lines. They're actually anti-parallel. these two lines are anti-parallel. One is going from left to right, the other from right to left. And if you compute the vorticity in this, using this approach, you find that essentially it is almost zero. So the scale here is gray, it corresponds to something close to zero. It is not exactly zero because the lines actually were, they had some superimposed wiggles, as you can see there, just to give some signal, okay? At the bottom, there is the same process repeated, but now the vortex lines are parallel. So you see here now a big signature of the vorticity. Two lines oriented together, parallel to each other, means that the velocity field add up and you have double the circulation. So you have really some vorticity field. And if you do that, you can actually find that the tangle actually behaves in a classical fashion. You can actually discover that this kind of box full of ink, if you plot it, contains some structure. So there is some physics inside. So at the top right-hand side, you see an energy spectrum. And you see how the energy distribution, the spectrum depends on the wave number. And here you see this decay, which this is log-log as the other picture. So the decay is like with the power of -5/3. So it's a classical decay. And then it's some length scale here in the middle, the slope changes and becomes -1. -1 actually is what we expect. It is the spectrum of a single vortex line. So we're looking at very short length scales, and you just see the vortex, the closest vortex in front of you. So this crossover from -5/3 to -1 happens at the scale which corresponds to the typical distance between vortices. So the turbulence is, in some sense, classical. We can actually say or speculate that we have actually achieved something. We have produced what is the skeleton of classical turbulence. Of course, classical turbulence does not contain vortex lines. It contains smooth eddies, plus some actual vortex tubes also. But clearly, this is a classical result. The second curve, which you see at the bottom, is actually the spectrum of the vorticity. And the vorticity in classical mechanics has its own spectrum, and it is actually gross. So it's concentrated at the large wave numbers rather than the small wave numbers, which is the rule for the energy. It grows like to the k to the 1/3. And indeed, this coarse-grained vorticity does exactly this job. So that is how we can actually try to make sense with the spectra and coarse-graining vorticity. We can make sense of our calculation. And we can actually...
Small question.
Yep.
You said that vorticity concentrates a small wavelength there. Is it due to the fact that you do the coarse graining?
No, this would be a classical result. You would see exactly this k to the 1/3. Mm-hmm. So there is more contribution at small length scales, large k, and then there is the viscous cutoff. Here, essentially, you reach the so-called Kolmogorov length scale at which dissipation takes over. The coarse graining scale is arbitrary. Yeah, it has to do with the coarse graining is done on a length scale which is actually proportional to the typical vortex separation, because that is what you want to pick up to define the vortex. So I'm going to say more about this. Indeed, in this using these figures. Here we try to answer the question why there is this Kolmogorov spectrum, try to get more insight. So at the left, you see another vortex tangle. A snapshot of the vortex tangle, you see all the lines in your box. And the lines now have been color-coded. And what's the idea? The idea is actually to color with this in yellow the vortex lines in regions where actually there is much vorticity. So the lines are parallel to each other, they're polarized. And in red, we color in red the lines where the vorticity actually is not there, okay? So we distinguish between polarized lines and unpolarized lines. Now the threshold, the distinction is based on some arbitrary cutoff, of course. And we can play with this cutoff. And indeed, what we find is that if you include all your vortices, so both red and yellow lines, then you produce something which is consistent with the classical Kolmogorov spectrum. If you remove the unpolarized lines, if you remove the random lines, you're left with the Kolmogorov spectrum. If you remove the polarized lines, you're left with a spectrum which is very different, which is essentially the Vineland kind of spectrum of the previous pictures. So that essentially explains why we have the Kolmogorov spectrum. It comes about because at any moment there are vortex lines which, by the dynamics, have come together in a parallel fashion. They may not stay. They will not stay there because these loosely polarized bundles are metastable, but they will keep forming and disintegrating and reforming.
How do you find bundles? How do you define bundles?
Well, a bundle, where it's a region. Yeah, the threshold, the sensible threshold is clearly the scale of the vortex distance, and you can play with this threshold, and you will see that where essentially the bundles are these yellow structures. Okay?
So do you use 3 distances? Can
no, the typical vortex distance, you can work it out from simply the total length, and you can scale it. You can find
once you exceed this, you obtain a bundle.
Yeah, it's clearly a smooth effect, of course. I also want to stress that most of the vortices are actually red. Okay, so the polarization is actually some kind of effect on top of a great amount of randomness. But of course, it makes a big difference because look at this cartoon here. Here we have 4 vortices all parallel, so the velocity field adds up, and we have a large flow. And here we have actually 2 vortices up and 2 down, and then you have a cancellation. That is to say, you don't have much energy, you don't have much vorticity, you have essentially the red lines. Okay, so now let's consider a further description. We go up the next level. So the next level is the level of the HVBK equations. So these are the equations which generalize the original equations of Landau to the presence of vortex lines. So the equations of Landau predicted, for example, second sound, but they did not contain vortices. Now the equations were written, as I said before, first by Hall and Wiener in their famous 1956 paper. If you want to see actually, but they wrote down the equation using physical arguments. If you want to see a derivation, which is actually more formal, I suggest this paper on the Archive of Rational Mechanics and Analysis, this paper by Hills and Roberts. So what are the equations? Essentially, they are equations for 2 fluids, Vs and Vn for the superfluid and the normal fluid. But here we must be careful because what they describe is actually a 2-fluid system containing a continuum of vortex lines. So we have lost the discrete nature of the vortices, of the quantized vortices. We are at the level of the forest. We don't see the sticks. So we are looking at somewhat length scales much larger than the distance between vortices, between the trees. So you see what the equations look like. So at the left-hand side, there is the usual acceleration of a fluid particle for the normal fluid and the superfluid. Then the first terms at the right-hand side contain some efficient pressures, which I did not write because they're quite long to write, involve the entropy, the temperature, and the actual pressure. And those terms would be responsible for well-known effects like the fountain effect in liquid helium or the mechanic caloric effects. And then at the right, there is an extra term, F and S, which is the famous friction, or better, mutual friction, because it affects both fluids. So it's the same, if you want, the same force coming onto both fluids. And you see actually that the friction is parameterized by the density ratios, ρn divided by ρ, which is the ratio of normal fluid to total density, and ρs divided by ρ in the other fluid, where ρn and ρs sum up to the total density, which is ρ. So if you take the limit of 0 temperature, ρn over ρ is 0, and you're left with the Euler equation. The top equation is the Euler equation. If you take the limit of high temperature, rho s divided by rho will be 0, and the second equation becomes the Navier-Stokes equation. So I said this model describes a continuum of vortices. So clearly the vorticity, again, is some kind of coarse-grained vorticity. And here again I've sketched the same idea. But I put a little cube around the vortex lines. And the cube here is not for visualization. The idea is that this is actually a small fluid parcel or fluid particle. It's actually the object whose acceleration is described by the left-hand side of the equation. Okay? So the little parcel of fluid must contain many vortices. And this operation of constructing the vorticity is not difficult to define. I suggested a method before with this Gaussian dressing of vortex lines. You can do it actually in a much simpler way, simply by counting, by defining what is a fluid parcel for you, and counting how many vortices are aligned along x, y, and z. Or better, measuring the length of the projections of the vortices along the x, y, and z direction. Then if you get this projection, you multiply times the quantum of circulation, you get vorticity. And you can create a vorticity field vector, because it's a vector, and then at each location, each fluid particle will contain its own vorticity. So you have a classical vorticity. So if you look at this equation, you find that it has actually some interesting features. The first thing is that there are two fluids which act upon each other via the friction. So actually the equations are fully coupled. So we have something which is more similar to the MHD dynamo than the actual Navier-Stokes equation for turbulence theory. So we have a two-fluid system. And we can actually then also proceed in the historical way in which the field of dynamos proceeded. Given the great complication of the physics, given the lack of computers, people looked at what happens, questions. They asked what happens to one field, say Vn, if Vs does something. What happens to the velocity if the magnetic field is something, or vice versa. But of course, everything depends on this friction exactly, because it's crucial. It's the coupling of the two equations. So, well, there is a situation in which it is somewhat clear what is the friction. In fact, it is the situation described by the Holweinen papers, and it is the laminar case. So, the original physical problem was a simple bucket of liquid helium put in rotation, and that is the picture at the left-hand side. So we have a container rotated in a particular direction, and we know that a lattice of vortices is formed, and we're interested in various things there. For example, how we can attenuate a second sound propagating across, or we can be interested in the fact that this lattice can actually vibrate. It can sustain waves, Kelvin waves, for example. So in this case, we know very well what is the friction. It's described in these papers, and actually it's spelled out in all the kind of nasty details over there. It's quite complicated looking. Again, with these coefficients alpha and alpha prime, which have to do with finite temperature effects. And there is also another term to add, which is a tension force, by the way. So everything works very well. There is another slightly more complicated situation in which this friction works, and I want to stress it because it shows how far you can try to push this model. So the problem which here I want to consider is Taylor-Couette flow. So that is actually the famous textbook case of the flow between two concentric cylinders which are infinite in length, so we neglect end effects. And for simplicity, we keep the outer cylinder at rest, and we only rotate the inner cylinder. So it's a typical exercise given to students. Solve the Navier-Stokes equation, find the velocity field. And the velocity field is simply azimuthal, so the flow goes around, and one finds the particular form of the flow. And if you compute the vorticity, actually, it corresponds to negative vorticity for a clockwise rotation. So I'll put the vortex lines pointing down. Now, in classical fluid mechanics, this problem is well known. It's actually historically very important. It was solved in the 20s by G.I. Taylor, and he discovered that when the velocity of rotation of the inner cylinder exceeds a critical value, then a new flow appears. So the circular quad flow solution, which students find easily, is not stable. There is another solution which kicks in, which is called Taylor vortex flow. So it is axisymmetric. It consists of clockwise and anti-clockwise cells, which are sketched at the right-hand side, which are actually on top of the azimuthal flow. So the same question can be asked in the context of liquid helium. In fact, experiments were performed with this configuration, and this is a case in which, again, the Hall-Weinand equations work very well.
Are those vortex rings which are you see those things, you see, because if I continue them, they're vortex rings.
No, sorry, that's my fault. So I sketched in red the vortex lines. This blue simply gives an idea of the flow. So there is, at this velocity,
vortex ring, you see, because it's.
Oh, I see what you mean. Yes, it is. From that point of view, yes, it is. So if you look at this,
So it looks like you have
yeah, right. So
a stack of vortex
it
rings.
is a stack of fat vortex donuts. Yes, it's a stack of vortex rings of alternating polarity. That is what is Taylor quad flow. And actually, it's of course it can become unstable at higher velocity. It's nice. So the picture at the right-hand side shows the vorticity field, which is the curve of the velocity in the Hall-Weinand approximation, computed from essentially putting this computed by solving these HVBK equations. So this is actually for small angular velocity, so the vorticity is aligned down, and this is actually the Taylor vortex flow solution. So you see that actually at different locations, the vorticity field changes. So each fluid particle has its own vorticity. Yeah, it's a kind of wobbling behavior of the vortices, which is stationary. It remains there. So the Hall-Weinand equations can be clearly put to test very well. In fact, I want to stress that the predictions here is actually the prediction of the critical velocity. And this kind of prediction is tough. So somebody who was old enough to be able to tell me this said that in the 20s, when G.I. Taylor did his calculation, actually did something else, convinced everybody that the no-slip boundary conditions which we now apply to the Navier-Stokes equation are correct. Because if you actually just change a bit these conditions, you alter the critical velocity by a large amount. So it's a very
critical velocity.
Yeah, the critical angle, this omega c.
No,
so,
physically, it's not the Landau critical velocity. What is it?
No, this is the velocity. It's the velocity.
Superplate component, it disappears.
No. Critical velocity for the onset of this secondary flow. Okay, so it's a kind of very tough test to predict the critical velocity. So it can be done. So in summary, we are very confident about the friction in this laminar case. But things become more complicated if our vortex lines are not so neatly arranged. So we let them actually change the direction and from a fluid particle to fluid particle. But suppose they all scramble, like in the simulations of quantum turbulence, of which you've seen pictures. Suppose they're not polarized. Well, so then people thought of other forms of friction, and they boiled down to something which looks like this at the end. So there is some friction coefficient, alpha, we just keep that. There is a difference of the velocity fields, large-scale velocity fields. There is this quantity L, which is the vortex line density, the vortex length per unit volume. And the point is that this is somewhat related to the vorticity of the superfluid, which we can call kappa, the quantum situation times L, but not precisely, because it would be so if the lines were polarized, but they are not when the flow is very turbulent. Still, we don't know what to do, And so, lacking more information and lacking better theory, So this idea of using this friction has been applied. And for example, here I have two examples. Was put in the two-fluid equation, which you've seen, and put in a big solver, and isotropic homogeneous turbulence was studied in a typical box, and you see here some snapshots of the entropy of the superfluid and the normal fluid. And look, you can immediately see that they're very, very similar. Just look, for example, this tube, this superfluid vortex tube, sort of kind of being exactly where there is a normal fluid vortex tube. So somehow the two fluids tend to lock onto each other. So,
do you have bundles here?
yes. So remember, in this model, a fluid particle contains lots of vortices.
No, I understand,
yeah?
but probably
Yeah.
big regions.
These tubes are not actually very different from the tubes which you find if you actually solve the Navier-Stokes equation. At the right-hand side, I've chosen another example because that's another beautiful example. It's actually the problem of the propagating front. So this is an experiment which was done in Helsinki, in which one sees essentially a vortex lattice system which actually propagates in a rotating container, making a front. So it's moving upwards here, and you see actually the kind of zoom of the end of the front, how the vortex lines fan out. And by fanning out, also they're twisting themselves. But there is still a large amount of polarization here. So it makes sense to use this model. Right. This idea of friction, simple friction, was also used in other further models. They are actually, at this point, some people would call them toy models because we're moving away from physical reality, trying to capture some key features. One is shell models. Shell models of turbulence used to be popular a few years ago. So tons of papers were written exhausting the possibilities. Essentially, they are dynamical system models of turbulence in which you give up on describing the geometrical description of the flow, and you concentrate on k-space. And you want to have a resolution in k-space. So essentially, you see like the time derivative, you see viscosity term in these equations. And L stands for nonlinear. Here there is the nonlinear coupling of K modes, a typical triadic interaction between modes of, which appears in the Euler and in the Navier-Stokes equation. There is the friction in the simplified turbulent case, and then some forcing. So they're quite nice because actually they give much insight, and they can describe these two fluids acting upon each other. So they're still fully coupled. And I think the most recent attempt of using these models by Victor Lvov and collaborators had to do with the problem of intermittency, which is actually quite an interesting fundamental problem. So they're very simple, but actually insightful. And there are also variations, essentially continuous model rather than discrete. Shell models are like, in a sense, large-scale dynamical systems. Lit models, again, the work of Lvov, which has been used using this idea of friction. Okay, so let me go get, after this list of examples, what we've done. So we have these three descriptions: the Gross-Pitaevskii description level, microscopic, the mesoscopic, the Vortex Filament method, then the whole Wiener equation. So each description has its own difficulties and problems. For example, Gross-Pitaevskii does not model liquid helium. It actually lacks important features. If you look at the excitations of a uniform state, you find phonons, but you don't find rotons. Also, the vortex core is not as simple as Gross-Pitaevskii says. It's quite more complicated. It's more like a solid body rotation, perhaps, if one does the problem properly using quantum mechanics. But by doing so, one essentially one ends up with difficulties for which one cannot do any kind of hydrodynamics. So it's not simple. Above all, Gross-Pitaevskii applies only to a condensate at zero temperature or very close to zero. The vortex filament method, as I said, has problems in the sense that reconnections are done by hand. So various reconnections algorithms have been tried and tested against each other. There is no observable, however, which give enough information to disregard one algorithm rather than the other. They're all sensible and seem to work. But it's clearly physics which is added on top of the Biot-Savart. So we can call the ruling equation the reconnecting Biot-Savart model. Above all, the original model of Schwarz lacks in this respect the back reaction of the normal fluid onto the vortices. Sorry, the back reaction of the vortice on the normal fluid is not accounted. So the normal fluid is prescribed, but it must obey its own Navier-Stokes equation with some friction. And this is not a simple problem. And if we go to the Holbeinian description, well, the major problem there is that we don't know how to distinguish between the polarized and unpolarized lines. So clearly, if they're all polarized, then yeah, it makes sense to define our coarse-grained vorticity, the equation work. But if there is much unpolarization, if there is too much randomness, then that contributes to the dissipation rather than the vorticity. So the relation between the vortex line length or density and the superfluid coarse-grained vorticity is not clear at all. So since there are not many minutes left, I want just to illustrate some attempts to move away, to improve our models. So something which would be nice, and it is actually quite important work to do, is to extend the Gross-Pitaevskii description to non-zero temperature. So there is actually a very big current literature on the problem, the various approaches. Essentially, you get variations of the Gross-Pitaevskii equation called the stochastic or projected or truncated Gross-Pitaevskii equation. Actually, we have two great experts in this field are in the audience, Brachet and Kustulovic, so you can ask them. There is another approach in which, rather than essentially in which one adds to the Gross-Pitaevskii equation some kind of Boltzmann equation. So essentially, it reminds us that Navier-Stokes is not God-given, but actually it comes from some kind of Boltzmann equation. So we couple Gross-Pitaevskii to a Boltzmann equation for the thermal excitations. And I want to just show you which kind of results one can obtain with this approach. So what you see here is the simple problem of one vortex moving inside a simple atomic condensate. The condensate is three-dimensional, but it's squeezed in the shape of some kind of pillbox, which is easily done in the experiments, and the vortex is visible because it's a hollow, so you see the vortex there. It's placed initially off center, so it should actually orbit with some velocity which we can predict. But because of the finite temperature effects arising from this coupling by a Boltzmann equation with the thermal gas, it loses energy and spirals out. And you see actually here some computed trajectories at different temperatures. So here it spirals out slowly and here more rapidly because the temperature is higher. And one can map this behavior to the equation of Schwarz and essentially recover what would be alpha and alpha prime in the Schwarz model. So what is actually there is, if you want, a calculation, not a theory, it's a numerical calculation of the alpha and alpha prime mutual friction coefficient done from first principle. Really the very first principle, something which would be nice to be able to do in liquid helium. So another bonus of this kind of calculation is that you get some insight. Here, the plots which you see represent the top series, represents the actual condensate. So these are plots of the density. So red is high density, blue is zero density. So the condensate is, this is the view from the top of our pillbox. So red means high density in the middle. And you see the little vortex, this hole here. So vortex is a hole which goes around. Now the thermal cloud is actually not uniform, but it likes to go where the condensate is not present, so it's more dense on the outer part of the condensate and less dense at the center. But you can notice that actually there is clearly a signature here of the vortex core in the thermal cloud. So in other words, what this model is saying is that the center of the vortex core is filled with thermal atoms. Another direction to make progress, making bridges between these models, is actually to improve the vortex filament model. So we need to couple the Schwarz equation to some kind of Navier-Stokes equation. And there are at least two strategies which I can think of for making this coupling. So one is very local. So you essentially come up with a scheme to implement a friction generated by vortex lines, which are described in a Lagrangian fashion, so that actually the variables are the position along curves, on some Eulerian mesh for the normal fluid. And this very strong local forcing will generate structures in the normal fluid which look like these kind of jets or dipoles, if you want. But whether these structures are true or not, I do not know, because as far as I know, there is no experiment which has actually detected this small scale structure, unless you've done it last week. I suspect so. There is another approach which is actually slightly more humble. So remember that in the Holbeinian approach, we look at coarse-grained equations. So here, an example is shown here in 2 dimensions. So we have vortex points, which are these colored dots. And you see these red grids containing blue grids. So here the idea is that you're going to solve here the normal fluid Navier-Stokes equation on a grid, and then try to compute the friction on a region which contains enough vortices that you can think of them as the friction of the Holbeinian equation. So this is kind of coarse-grained. And
that's the actual grid.
Yeah, that's actually an idea. It's the grid. So you see the vortices are the red and blue dots.
So basically they're point-like.
Yeah, the vortices are points, Lagrangian. They move across our grid, so they will never be exactly the grid point. They're always in between. So then you define another grid by the blue squares, and then sort of a larger grid system, which is in green, where you try to compute your friction. And you can get interesting things, which make sense compared to experiments. You can get correct density profiles, etc. And then brings also the other problem that we have this separation of length scales to account in studying quantum turbulence, which is quite crucial to keep in mind. So when we deal with atomic gases, atomic BCs, systems are quite small. So here I've put some values typical of experiments. D is the system size. Psi is the size of the vortex core, or healing length, if you want. L is the distance between vortices. So in most experiments, the system is not much bigger than the distance between vortices. It's difficult to produce very, very large condensates. So the length scales, which are described micro, meso, and macro, they are separated, but not widely separated. Not like in ordinary turbulence. Now, we don't have a vortex core size in ordinary turbulence, but we have, because the vortices are continuous, but we have the Kolmogorov length scale, the length scale of dissipation. And when we define the Reynolds number, we define actually the number of linear degrees of freedom, because the Reynolds number can be defined as a power of the ratio of the large scale and the Kolmogorov length scale. So d divided by eta replacing psi in a viscous fluid, simply measures, as I said, the number of linear degrees of freedom. So that's huge in this particular experiment, Grant and others, 1 million. But when you take liquid helium, the similar number is even bigger. So it's That's terrifying, 10 to the 10. So this is really hard. So I see the time now it's coming to an end. So I don't know, this is a simple overview, so I've been quite biased in the choice of topics. So the thing to remember is that there are 3 possible levels of description with some bridges between them. And I'm looking forward to the rest of the week with talks. And for you to remember from today, well, just remember we have these 3 levels, and I hope the information I've given you will help you following the talks better. Thank you.
Thank you very much. We have time for a few questions.
If we have just a Gross-Pitaevskii equation with some turbulent motion inside, it produces also sound waves versus compressible. The short wave, sound waves will be thermalized. Now my question is, can I consider this situation as a two-fluid model in which normal fluid is compressible part of the so two-fluid mode is just inside of the equation itself.
Yes, in the sense, the Gross-Pitaevskii, as I said, we have the big experts of this. Was it one there? It is. I think it would lack, however, the ability to create a large-scale normal flow, correct?
It would be rather a gas.
And it's more like a gas.
Not a fluid.
Not a fluid. So it would not make things like this. Here, you see, okay, well, what is exactly this picture? There is a vortex line coming out of the page, so perpendicular to the screen, which is dragged, if you want, in this fluid gas and creates this circulation. So the model would not do that, but it would actually predict effects like the friction felt by this vortex line. Yeah.
Any other questions?
Can I get back a second to the Taylor-Couette flows? I was wondering, because I'm kind of thinking of the neutron star problem where the frequency is changing. If I start off with a frequency that's below the critical one, and then I end up with Taylor vortices appearing in the flow, this can stabilize the vortex array itself. But now
So you start with the...
I start with my straight vortices, and I'm below. And then if I end up in a situation where the Taylor vortice is formed, then I get flow along the actual.
Yeah, there is.
Why did you do that actually from the first to the second symmetry? The direction of the vortex is being flipped. Because now you have the observer.
Because if the rotation omega is positive, the vorticity is actually that. In fact, this idea has been actually taught. There are great difficulties there because we know so little about neutron stars. So to start with, I find it very hard to think that you have vortex lines with a structure size which is like helium, angstrom, with the typical rotation, which means a separation, again, like a helium experiment of the kind my good friend Liebig does, and it's actually 10 kilometers across. Then the other problem is actually the boundaries. The boundary conditions for the laminar Fulvinian equations are a bit tricky. Now Melatus is not here. He tried to solve this problem, but he avoided actually using this full friction because it introduces mathematical complications on a spherical boundary.
Yeah, we did a bit of work with that when I was in Melbourne.
Yeah.
But I guess my question was more related exactly to this problem. What do we actually know? What happens to the vortex array once I end up?
Well, so a small velocity. Okay, I can tell you how far the model goes. So this model, the Fulvinian-Bekarevic-Kalatnikov equations, were used to compute a critical angular frequency. It works. They were also used to compute in the nonlinear regime. So when we are in this regime, the torque, which was the only observation available, the torque on the inner cylinder, and we went up to something like, I think 12 or 15% above critical. And torque was correct. But at some point, the Taylor vortices destabilize. They develop wavy modes, they're called. So they're not axisymmetric any longer. They start wobbling and become time dependent. That may still work. It has not been tested. But if they become turbulent, then we face the problem that this friction must be replaced by that. And we're moving in a situation for which we don't have good experimental tests. I mean, a theory and an experiment on the same system being compared. So we are moving on ground which is more difficult. It would be nice to have more experiments and calculations which can together tackle this problem.
Thank you. All right, thank you very much.